Okay, hello everybody. So my name is Melvin. I'm product manager at a company called ClickHouse, like on my t-shirt. And today I'm going to talk to you about some of the work that we are doing in our database, right? And more specifically, how we are integrating open table support in our database directly. And some of the challenge that we met as we build this integration. So can you raise your hand if you know ClickHouse? Okay, can you raise your hand if you know Iceberg or Delta? Okay, so a lot of people, more people know open table formats than ClickHouse apparently, so I will briefly talk to you about what is ClickHouse. ClickHouse is an open source project. It's a database. It's a database specialized in analytical workload. It's a columnar-oriented database. The first prototype of this database was released in 2009, and it was first tried in production in 2012. And finally, the project was open source in 2016. And since then, a lot of people contributed to it. It's one of the most contributed projects on GitHub. It has over 40,000 stars. And it's one of the mainly used real-time analytical database out there. We created a company in 2021 which built a managed offering on top of this database. And in 2022, we released a cloud offering of this database. And when we developed this database, there was some components that were very important for us. The first one that ClickHouse needed to be extremely fast. And that was one of the core principles of the database, is it is built for performance and for low query latency. And for that, we created many different features, things like projections, asynchronous and synchronous materialized view, allowing to always go down in terms of query latency. We also added support for many data types, things like JSON, variant, data type. We have uint 8, uint 16. We support like a wide variety of data type, which allows a lot of flexibility when you're actually using this database. And given this database was supposed to scale and to be like open source replacement of Google Analytics, it was supposed to be able to handle petabytes of data, right? So we wanted to make some things that scale at a very large volume. And because we like simple things at ClickHouse, we wanted everything to be contained in a single binary. So that was kind of I would say, the main direction that we took when we built this database. But when you create a database, especially for analytical workload, this database needs to be integrated with a larger ecosystem, right? Because people want to put data in your database, so of course you need to make sure that people can access data from your database. So you need to make sure that people can access your data in your Kafka queue, or in Red Pandas. You need to make sure that they can read maybe your MySQL database or PostgreSQL database, or integrating with your data lake ecosystem. And today we are really going to talk about this section here. So the question is, we have our database, and before we had any support for open table formats, we needed to start building it. And actually, because of the, I will say, power of open source, we didn't have to do anything, because the first contribution to ClickHouse to support this open table format were done by open source users. People that use ClickHouse and people that use Iceberg, and they want to read their Iceberg table with ClickHouse, and they decide to do a pull request and support this format. And you can see actually these two pull requests, one was for UDI and Delta Lake, was done in 2022, and the second one was for Iceberg, which was done a little bit later in 2023. So you can see that there was a strong traction from the community to actually support this table format. But over time, we merged this pull request, of course, and we worked with the contributor to maintain it. But over time, as people start using their open table format, we can see that they start having challenge. Specification change, like Iceberg specification evolved, Delta Lake specification evolved, and things start to break apart. And people have like weird error when they try to read the table. So we decided as we have many developers that work on ClickHouse at ClickHouse, and we were like, okay, we need to make this integration much more stable. So we spent the last year or so working on it. And we have focused on mainly leveraging the ecosystem on making sure that our integration was compatible with this open table format. And we took two different angles. The first one was to make sure that data were easily discoverable. And we worked a lot with catalog to make sure that when you want to read an iceberg table, you don't need to specify your S3 buckets with the credential of your S3 buckets and all of that, because it's a very cumbersome process, but you kind of always go through a catalog, you identify to the catalog, and then you can read all the different tables that are behind your catalog. So that was the first effort that we did, was integrate with catalog. The second one was to make sure that ClickHouse never break with your open table format. And for that, it requires to make sure that we are following specification. And this is difficult because ClickHouse is developed in C++, and as of maybe 1 month ago, there was no C++ library for Iceberg. And there was no ecosystem for Delta Lake as well, right? So we, like a group of people from Databricks and Microsoft, get together and started building a solution for Delta kernel, which I'm going to talk about briefly. And this solution helped us a lot because basically this was a Rust library, and this library was basically supposed to handle for you the Delta specification. So all you have to do is provide a reader to specific files, and this library you can embed it into your project, and it will do all the understanding of the specification for you. So the developer of Delta just have to maintain this library, and you just have to make sure that you can read the different file that you are supposed to read. And that helped us a lot. So this is a project that was incubating for quite a while, and that we are now using in production. And actually, the concept is very simple, right? There is different APIs that you can interact with, and there was some challenge for us because ClickHouse is C++, this library is Rust. So then we need to start like thinking about how to take a Rust library and put it into a C++ code, which had its own interesting discussion about all of our CI and all of our testing pipeline. But overall, it helped us a lot because now we have libraries that can process your Delta specification without us having to always maintain it as it keeps evolving. And the second area we worked on was integrating with the catalog ecosystem. So here you can see we started supporting, like REST specification for the catalogs, Iceberg catalogs, and all we had to do was follow the specification, and all of the catalogs suddenly start working together. So we had Glue that we could integrate with very easily, Iceberg REST catalogs, so including Unity, Polaris, Nessie, that worked out of the box just thanks to this specific integration. But one of the, I will say, most difficult components that we had to do is around Iceberg table, because we didn't add a library for it. We had to re-implement everything from scratch. And that was kind of challenging. So in order to understand the challenge that we had to go through, I'm going to talk to you about how data works in ClickHouse, because it's important to understand how the format of ClickHouse is compared to Parquet. And then you will see that actually the formats are very close. And most of the features that we needed for ClickHouse, that we needed for Parquet, we already added for ClickHouse. So I'm going to show you how data are stored in ClickHouse, and you're actually going to understand, why Parquet is that way. It's actually like you will see the two formats are very close to each other. So when you insert data into ClickHouse, we are going to do what we call a part. And a part is just a set of files, immutable file, that we are going to store on disk. Let's dissect what's in these files, right? So the first thing we are going to do is we are going to take your data and we are going to sort them based on a specific key that you can specify. Once these data are sorted, we are going to write them compressed on your disk, and we are going to write one file per column. So if your table has 3 columns, you are going to end up with 3 compressed files. Now the question is, how do you read efficiently from these 3 compressed files? Right? Let's say you want to retrieve a couple of rows from this file. How do you do it in an efficient manner? Well, you are going to do it by creating an index. And creating an index is not a trivial task unless you have a good data organization. So remember I told you that when we are inserting your data in ClickHouse, the first thing we are going to do is sort your data. So ClickHouse is going to create this sorting in memory and then going to write it on disk. On top of this sorted data, ClickHouse is going to create what we call a bunch of mark, right? So it's basically a sparse index. It's going to look at the first 3 rows and it's going to tell you, okay, we are going to have our first mark that is going to go from 0 to 2 to 3 to 5, etc., etc. You can define how granular you want your marks to be. And then we are going to use this mark to create an index. So for example, for the first mark that we have here, we are going to say, okay, this mark starts with Barcelona, right? Because this is sorted. So we can say it starts with Barcelona. The second mark starts with Lima, for example. And the last mark starts with Sydney. And then we can use this mark to actually do a binary search, which will be very efficient, and actually retrieve the data that we need to read very efficiently. So let's do a simulation of how we could actually read this mark. So ClickHouse is going to go to this index that contains all of your marks. We are going to write this index on disk, and we're also going to load this index in memory. Right? So let's say I want to find all the rows that contain a city called Montreal. We're going to check the primary index. The marks are sorted because your data are sorted, and we can very quickly find which granule the row is in. And here we know that it's in the first granule. But here there is a problem. The problem is my data are compressed, right? So how can I read my compressed files just based on the mark? So it's a first challenge. So ClickHouse create more files. It's going to, when we're going to write the data, we are going to write the data per block. And a block is basically a certain amount. You can see that as a pages in Parquet. So it's just a set of rows that is around 1 megabytes approximately. And a block can contain multiple granules, or like a granule can contain multiple blocks. There is no relationship between them. And we are going to be able to use this block to create a mark file. And basically the mark file will contain a pointer to a specific blocks on a specific granule in a specific file. So remember, this is my compressed file. This is a corresponding mark file. So I know that I have my first mark that point to granule 0. And the mark file is just going to register the offset of my block in the file and the offset of my granule in my block. And now, when I actually execute a query, I'm going to search all the rows in my table where the city equal Montreal. So the first thing we're going to do is still going to my index. From this index, I will go to my mark file. So I know that I need to read the mark 1, for example. So I'm going to go into the different mark file, find the mark, find the offset of my block, and find the offset of my granule. So now I don't even need to read the whole file. I can just read a section of the file that contains the data, and then the section of this block where my granule are actually located at. And now I can actually very efficiently read my files. So in the end, you can look at how ClickHouse works, right? So for for a table with 3 columns, we had to create 1, 2, 3, 4, 5, 6, 7 files. That's a lot of files. So what do we do? And especially that's not all the files, right? Because if you look at, if you add additional skipping indices, ClickHouse will create even more files, right? Let's say, for example, you have a column in which you want to do min-max filtering. ClickHouse will be able to do the same behavior, create granules, and then create some type of index where we point to a specific granule in order to skip some rows, right? So if you have like a more complex query, we can skip rows and we can skip rows into a different files. So it creates, in the end, a lot of files. This is the first part for file format that ClickHouse created. It's called wide part. Wide because if you have a lot of columns, it's going to have a lot of files, right? It's going to have 2 files per columns, 1 primary index, and a bunch of files for each skipping indices that you are going to add on top of your columns. And that has some benefits, like you will have very good read performance because you need to read only 1 file per column, for example. But it has also some limitation. One of the first limitations it has is when it comes to cloud storage, right? This is very good for local disk, but when it comes to cloud storage, each one of these files will be stored differently, and that might increase ultimately your latency, right? So that's the first problem. The second problem that it has is that it's like, as you add more columns, it will create more files, and during insertion time, it will use a lot of memories to write all these files. So that's a problem. So we thought about it, and then we decided to create a new file format. We created the compact part format. And basically what this compact part format is doing is that it's going to take multiple columns and compact them together into a single file. We're going to do the same thing for our mark file. We're going to take all of our mark file for all of our columns and compact them into a single file. So now we reduced a lot the number of columns that we require in our storage. We still have 1 file for the primary index. We still have like some file for the skipping indices, but now you have like only 1 file for all of your columns, and that's much better for cloud storage. So when you look at compact parts, you can actually look at Parquet files, right? And you will see that there is actually a lot of similarity into how it's done. If you look at a Parquet file, the Parquet file will contain what we call a row groups, which is a bunch of rows put together, and these row groups will be divided in column chunk. So you are going to have like 1 chunk for each one of your columns, and each columns will be divided into pages, which will contain a bunch of statistics. It will contain statistics about the data that are stored in these specific pages. And then you are going to have your next column with like different pages, etc., etc., and you're going to have like all of your row group that will be stored in a single file. So there is a very strong correlation between what ClickHouse has. So for example, ClickHouse will have parts, which is a set of files. Well, in Parquet, that will just be the whole Parquet file. Your whole Parquet file will be a ClickHouse parts. Then if you look at the ClickHouse, actually ClickHouse has block, and in Parquet you will have like page, which is just a set of rows grouped together. And same thing, we are going to have like skipping indices in ClickHouse, and in Parquet you will have like a page level indices. So when ClickHouse executes a query, it's going to use the inverted index, it's going to use the index, it's going to use the skipping indices, it's going to read some statistic files as well, it's going to read some metadata. So all the components are here, but a lot of our work was to actually adapt our ClickHouse reader to the Parquet file. And actually we also discovered that Parquet has a lot of interesting optimizations that ClickHouse do not have. Most notably, for example, the footer. When you read a Parquet file, you will always start with a footer, which will contain information about, which will contain metadata about your whole Parquet file. And it will be much more easy to actually read the Parquet file because you start by the footer, and then you don't have any offset to take into consideration when reading the file. And that was not the case with ClickHouse file format, because in ClickHouse file format, it was at the header, and we had some performance bottleneck right here. So this is kind of, so all these components that we had in ClickHouse, we had to rewrite them and to actually apply them to reading this Parquet file. And it's not a trivial process, because it took us a lot of time to actually come back with a proper solution. We started with the first Parquet reader, which was very poorly optimized. We had a second Parquet reader, which was a bit better. And then we ended up with a third, we just released like our third Parquet reader, which this time is much more optimized and take into consideration all the statistics that you have in your page statistics, but also all the statistics that you have in the various metadata of your Parquet file, including Bloom filter, min-max indices, and so on. Great, so that was, I think, the main challenge that we had. So now, with all this work that we have been doing, where do we stand? Well, now ClickHouse supports, and I think that we did that across maybe 10 months. Now ClickHouse is able to read Iceberg table up to V2 version. We still don't support some of the latest developments like deletion vectors, for example, which are additional specifications that we didn't take into consideration. One of the regrets that we have is that we just finished the development, we just finished our sprint now, and we recently saw that a new C++ library for Iceberg was released, like maybe a month ago, and that made us sad because we spent we spent a lot of time actually building all these building blocks that actually reads the metadata layer. Sometimes it's a bit painful. So now we are thinking about, should we switch to this official library, or should we keep iterating on our own library now? So it's a bit of a bummer, but we actually spend a lot of time on this Parquet reader. So now we have support for most of the data type in Parquet file as well, up to the GeoParquet. We can process GeoParquet files since the last index. So yeah, that's kind of a summary of the journey that we took from a SQL database that has its own, own format, which is our ClickHouse native format, which has a lot of optimizations that Parquet doesn't necessarily have. For example, if you can see that ClickHouse has two types of parts, right? We have the wide part and we have the compact parts. Compact parts are very good for insertion workload because you have much less files to write. And over time, as we are doing compaction on our files, we are moving to wide part, which is much more optimized for read, right? So some of these optimizations are not present in Parquet, but this is kind of represent a lot of effort to support. So I thought it was interesting to come here and talk to you about some of our story and some of the limitations that we encountered during the development of this feature. So thank you very much for attending. If you have any question, please, you can come find me here, or we have a booth a little bit further down there, I think CAN 19.8. So if you want to go see us, please pass by and say hello and ask any question you want. Thank you.